Okay, hello everybody. Thank you so much for taking the time to spend the next hour or so with us. This will be an introductory lecture on glass ceramics nature, properties, and processing. Regarding questions, I think you can stop me at any time. Just use the box right down on the left-hand side of your screens and raise your hands and make questions. Let's see. I'll do my best. Try to answer that. So okay. Thank you, Himanshu, Bill, and Carlo for inviting me. This is an honor for me to participate in this experiment. For me, it's an experiment. This type, using this technology, this type of lectures online. I confess to you, it's the first time I do it, and I'm a little bit nervous about the internet connection, but except from that, I think we will be okay. Hope that my internet works okay. Let's then move to slide 2. May take some time for you. Bill, guys, can you see slide 2? Maziar can. Thanks, Maziar. So, I'm in Brazil. This is the map of Brazil. Let me try to use one of these tools here. Yes. See, can you see the little finger? Yes. It's the map of Brazil.
You must, don't forget, left mouse click on it so we can see it.
You cannot see it yet?
Not yet.
Ah, now you can see it.
Yes.
Yes? Okay. We are here, state of São Paulo, southeast of Brazil, and the capital, São Paulo City, is shown here in the other map, not far from the Atlantic Ocean, and we are here, São Carlos. So this is only, say, 24 hours from Lehigh, or 36 hours from India or from China. Not far away, just 1 or 2 days away, and you'll be here. So that's why we want to make use of these nice internet tools to be able to teach and to chat and to discuss different subjects. This is our university, Federal University of São Carlos. And below you see our lab, and that's where I am right now. You can see this is the window of my office. I'm sitting right there giving this lecture. That's wonderful. I'm sitting there and you're listening and seeing this lecture miles and miles and miles, 24 hours away from here. So that's why I'm really, really excited about this lecture. I have no feedback, so I assume that you're all on slide 3 and seeing everything I'm trying to show, right? I'm waiting
all
for
good.
an answer here.
All good.
Okay. That's one difficult thing about this type of lecture. I have no feedback. So I don't see if you're happy or if you're angry or if you're sleeping. So I hope for the best. Okay. Well, the current lectures, there'll be one lecture today and the next lecture on Tuesday, same time. It's a total of 2.5 hours. This is a very small part of a course that I normally teach once a year here in São Carlos, dealing with the Vítreo state. In this particular course, I talk about glass structure and glass nature and properties, glass structure, relaxation phenomena, including glass transition, liquid-liquid phase separation by nucleation growth, spinodal decomposition, and everything else. Then crystal nucleation kinetics, crystal growth kinetics in supercooled glass-forming liquids. And then a combination of these two phenomena giving overall crystallization, the DeMA equation and other equations which deal with overall crystallization. After this part, this fundamental part, we move to some applications of nucleation growth in glasses. Sintering of glass particles with concurrent surface crystallization, critical cooling rates for glass formation, which can be calculated or measured from the nucleation growth rates, glass stability against spontaneous devitrification, and finally glass ceramics. So, in these two lectures, we'll be dealing with only this final part, 2 hours or so, of a more complete course. If you are really interested in this subject, we decided with the American Ceramic Society to do a shorter version of my course. It'll be 8 hours focused on the fundamentals and applications of controlled crystallization of glasses. That course will be taught jointly with the Glass and Optical Materials Division meeting in Miami in May. So if you are interested, you check in the webpage of the American Ceramic Society. This will be an 8-hour, so not as extended as my original course, but enough length to cover more than you're going to cover in these 2 lectures. So I hope you now understood that here we have 2.5 hours divided in 2 lectures, just to give you an idea. This would be an idea, an overall idea of different processing techniques used to produce glass ceramics, some of the critical issues, and some applications of these really, really wonderful materials. Their nature, their properties, their applications, and different processing techniques that are used to produce these materials. So I understand that a good deal of the processing of glass ceramics has to do with the processing of glass. So one starts with high temperature reactions of the chemicals, then melting, and then homogenization of a very, very viscous melt, because I guess you know that all good glass forming materials, they are good glass forming materials because the crystallization rates are so slow that you can cool down a liquid without crystallization. And it's normally so slow because the viscosity is so high, even at the liquids or at the melting point of the material. So we are dealing in most situations with highly, highly viscous fluids, and that makes the lives of glass-making people very difficult, because it's so difficult to get homogeneous, chemically homogeneous melts. It's very difficult sometimes to get rid of bubbles. Fining is a very complex, troublesome process, and these have been partially covered in previous lectures. Also glass forming technique. After you make a good glass, a good bubble-free homogeneous glass, you have to shape some glass article. There are many techniques to shape the glass article. Then the glass ceramic processing techniques start. It starts normally, in most cases, with a shaped article. So one has a shaped article in its final format, and then one has to devise clever ways to induce crystallization in the volume, in the interior of that piece. That's what we are going to talk about today, how one can design the composition, the thermal treatment to induce crystallization in the bulk, in the interior of a shaped good glass article. Okay, we will give, for the sake of completeness, the definition of glass ceramics, what they are, of their nature, a little bit on this history of glass ceramics, their main properties, and applications. And in doing that, I'm going to also introduce yes, I see that people cannot hear me. I am on slide 7. Yes, I am on slide 7, Bill, and the volume of my microphone is at the maximum. Everything here is at the maximum I can. So
you might try putting your microphone closer to your mouth.
It's really close. It's like a few microns away from my mouth.
Okay.
You can see it here. So
I'm hearing you fine.
You are hearing me fine. Akyar is saying, okay, Edgar. Does anybody else has problems with the sound?
And make sure you turn up the volume. Everybody else, make sure you turn up the volume on your own speaker. Use the volume adjustment on your microphone, on your Windows.
Well, see, most people, even Andrea can hear me now, Andrea. So I think most people can hear me. I'm very close to the microphone at maximum volume. I cannot do better than that. Paulo can hear me. Okay, so I guess I'm going to continue, but please let me know if you find further problems. Right. We are going to talk about thermal treatments. One can use a conventional furnace, electric furnace, for thermal treatment, or you can use also a microwave furnace or laser heating. There are several ways to heat, to transfer heat from one source to the other and to heat the material. I'm not going to go into details on all the different devices that are available to heat treat glass ceramics, but I will focus a little bit on how you can choose appropriate thermal treatments. It can be single, double, triple, even 4 different heat treatments to produce a certain microstructure which will lead to some required set of properties. In the core of glass ceramic research and development is exactly on the development of adequate micro or nanostructures. It is the combination of a given chemical composition with a certain heat treatment to develop desired micro or nano structures which will give some properties. For instance, the grain size distribution, the number of crystal phases, the volume fraction of each crystal phase, the volume fraction and chemical composition of the residual glass phase. Glass ceramics almost always have some residual glass phase there, which is very important for the overall set of properties and applications. So I'm spending a rather long time in the introduction because I'm not sure that everybody's really familiar with glass ceramics. And as I said, I don't have a feedback from the class, so I'm hoping I'm giving a lecture to an average glass scientist, which is not the real expert on glass ceramics, but I guess there are many people who are experts, so I beg your pardon here, but I have to do an introduction. Anyway, I gave you, for the students who are registered, officially registered, I gave you some reading assignments, and I picked this particular review paper. This is not the very best, but I like it very much for the simple reason that I wrote it. So I used this bias criterion to choose this paper as a good one, as a reading assignment. And I also like this book here very much, from my friends Wolfram Holland and George Buell. It's a very good textbook if you're going to work on glass ceramics. But there are other textbooks that I'm going to direct to you in a minute. Anyway, let's start then with the overall properties of glasses first. Inorganic glasses, because there are organic glasses, there are polymer glasses, metallic glasses, and all sorts of exotic glasses. I'm here talking about the old-fashioned inorganic, mostly oxide glasses. They're isotropic, which is a good property. They can be transparent, opaque, colorless, or colored with any color. Refractive index can be such by playing games with the chemical composition to vary significantly from 1 to 2.5 or so, 2.3. They can be electrical insulators or really conductive, ionic conductors. Their glass transition temperatures can vary a lot. I mean the laboratory glass transition temperatures that you measure with a DSC or a dilatometer from 100 and few degrees Celsius to 1200 degrees Celsius, for instance, for pure silica glass. The thermal conductivity is always low due to their disorganized, amorphous nature. The funnel mean free path is always small, so the thermal conductivity is small. Their hardness can also vary a lot, from 3 to about 15 gigapascal. I'm not sure if one glass can reach, maybe a high alumina glasses can reach about 15 gigapascal hardness. And they can be really chemically durable or can dissolve in water. Anyway, this set of properties is really, really good, and that's why glasses are extensively used everywhere in our lives. But they have, unfortunately, some negative properties. And one of them is fragility. Glasses are really fragile. They do not stand mechanical shock. They shatter, they break. And also, in addition to that, the fracture of glass is really dangerous. It's due to its conchoidal fracture that the very sharp edges are produced, and they can be dangerous. They are also metastable materials. They somehow, we avoided crystallization, and that's why one can make a glass, but they tend to crystallize more or less. And that's what we call stability against crystallization. Once you made the glass, Some glasses are really stable, other glasses can devitrify. Uncontrolled crystallization can happen. And these are in the very core of glass properties. We had a recent paper with John Mauro, published last year, 200 Years of Glass Research, and to our great surprise, to me and John, the most frequently used keyword in glass history, in published scientific articles starting in 1850, is what? Crystallization. This is the most frequent keyword. Another very frequent keyword is nucleation, crystal growth, and glass forming ability. So if you see this figure in total, crystallization-related phenomena are the most frequent phenomena related to glass research in the past 200 years of glass history or so. This is really interesting. And why is that? Well, if you look at the very famous old book authored by George Morey, first edition was published in 1938. The second edition, I have the second edition in my office, 1954. The properties of glass. In one of the first chapters, he says, the vitrification is the chief factor which limits the composition range of practical glasses. And he is right. He is right. Now, many potentially interesting compositions cannot be made easily into a glass because they just crystallize so fast. So there's a big game in the glass industry. Engineers know that very well, and glass industry researchers know that chemical composition has to be controlled within certain rigid bounds to avoid spontaneous crystallization. You don't want, nobody wants spontaneous crystallization if you're going to make a glass. So according to George Morey, it's an ever-present danger in all glass manufacture and working, and takes place promptly with any error in composition. So this is one of the reasons why crystallization is an important phenomenon in glass science. People want to avoid crystallization in order to make a good glass. There are books, there are book chapters, there are many papers on heterogeneous surface nucleation, which spontaneously happen when you heat a glass piece. And by far, 99.9% of the known glasses, they will crystallize from the external surface if you heat them up a little bit above their TGs, their glass transition temperatures. Very, very, very few compositions are able to crystallize in the volume, in the bulk. But that's what one wants for glass ceramic. You want the whole thing to be crystallized uniformly in the interior. So this is the game of glass ceramic making. And the vitrification it's one of the major causes of defects in glass. Oh, I guess this phrase here.
There's a question for you, but I would also like to ask that the attendee who has his video and voice on, please shut that off, please. Yes, up here.
Okay. Professor Zanotto, how do ceramic glasses compare to tempered glasses in terms of fragility and stability. Richard, could you please remind me and ask that question a little bit later on? I'm going to talk about mechanical properties of glass ceramics and strong glass ceramics. So if you please be patient and remind me again later on, and I'm going to answer. Otherwise, I'll have to stop my reasoning now and escape a little bit from my own subject now to answer. But, okay, later on, I will try to answer your question. So, I was talking about spontaneous crystallization, which most of the times start from the glass surface, the external surfaces of a glass article, because there are impurity particles, there are broken bonds, there are scratches, there's all sorts of possibilities for heterogeneous nucleation. So that's where spontaneous crystallization normally starts. That's normally unwanted. It's a source of defects. And people spend times and years studying surface crystallization. I'm going to talk about the TC7. There is a Technical Committee 7 of the International Commission on Glass. They have been working on glass problems for about 40 years. 40 years, and they spent about 10 years only focusing on surface crystallization. They have published a book. It's very interesting, and I can give you the reference later on if you are interested. So, to continue my reasoning, let's take a look at the discovery of glass ceramic. You know that natural glass ceramics really exist. I have pieces and pieces of obsidian. I'm really crazy about obsidian. Let me try to show you one here. See, this one is right in my hand here. You can see that these are materials from volcanic origin. They are magmas which have partially crystallized. They have some types of unmolten materials, and they have solid particles which somehow led to crystallization in the bulk. They're partially crystalline. You see here the gray crystals embedded in a matrix of black glass. These are natural glass ceramics. And they always exist. They have geological ages. But one guy in France, Rémieux, in 1736, had a nice idea. This guy wanted to make a porcelain vase. And he had this brilliant idea. He had a bottle of glass and inserted that bottle of glass in a sand bed inside the furnace and heat it up. So let me ask you attendees, what do you think it happened then? What happened to Rémieux's bottle some centuries ago? After heat treating for some time above TG of the malt, say at 600 degrees Celsius or so, for some time. Let me see some answers. I'm asking you this because I'm not sure if you are sleeping or not, so I want to see how many people are awake. No answers. Andrea, let me ask you then. Are you still on? What happened to that bottle that Rémieux used more than 200 years ago? after, say, 1 hour or two in a furnace at 600 degrees Celsius. Nucleation starts. It deformed somewhat, ceramized. The color changed or crystallized. I also think there could be deformation. Change the color. Yes, guys, you're excellent students and attendees and professors. Andrea is a professor, by the way. It deformed. It crystallized from the surface a little bit, partially crystallized, but the residual glass completely deformed. So he ended up with a partially crystalline material but completely deformed. It was no longer a bottle. That was a very interesting experiment, and he published that paper. I have the reference somewhere in the proceedings of the French Academy of Sciences or something like that. He published that paper, and he shows all the details of the experiments. But he did not realize at the time that glasses tend to crystallize from the surface on defects, on impurity particles, so it's not uniformly distributed within the glass volume. So 200 years later, this very important person, Stanley Stuckey, who unfortunately passed away on November 4 last year, was 99 years old. He was. In 1953, he was a young researcher at Corning. That's one of his pictures here, Corning glass at the time. And he was working with a lithium silicate glass which had metallic silver particles, nanoparticles of silver. He was working with photochromic glasses, this kind of glasses. And he accidentally, one of his furnaces went up to 900 degrees Celsius instead of 550, 600 that he wanted to, just to anneal the glass. And, okay, he saw the mistake and tried to pick that glass sample out of the furnace, but the glass dropped on the floor and did not shatter. Did not shatter. So I'm starting to answer that question. Glass ceramics in general are much stronger than glasses. It had crystallized on top, crystal phases formed on top of the silver particles which were dispersed in the volume of the glass, and he made the first artificial glass ceramic in 1953 or so. And then Dr. Stuckey and his colleagues at Corning, they spent maybe 4 or 5 years trying a huge number of other compositions, trying to crystallize other crystal phases which had particularly interesting properties such as cordierite, diopside, and lithium disilicate, and several spinel and several other phases. And so they started to file patents and things like that. I think their first article, scientific article, was only published in 1960 or so, 59 or 60. So they spent a lot of time protecting their invention and developing many, many other glass ceramics. And if you look at Wolfram Hullen's and George Beale's book, they say that knowledge of the literature, good observation skills, and deductive reasoning were clearly evident in allowing the chance events to bear fruit. In other words, okay, was an accident, but he was alert enough and an expert and a scientist, really alert scientist, because perhaps for some of us, this glass, the piece of glass ceramic would drop, it did not shatter, you'd say, oh, it did not shatter, so what, and forget it. So it was an accident, but this combination of knowledge and skills and alertness allowed the chance events to bear fruit. And I fully agree with George and Wolfram that he had a great contribution on that. It was not a pure accident. So we owe a lot to Dr. Stuckey, and I'll be talking about more, a little bit more about him in some further slides. I only met him, unfortunately, once. This is the photo. This is Dr. Stuckey here. We had a symposium on crystallization in 2006 in the USA. And these guys here, the TC7 members at the time, the crystallization committee members at the time. And he was about 90 years old already, and he accepted our invitation, and he came down to Stone Mountain and participated in the meeting with us. This, of course, is George Peel, another very important scientist on glass ceramics, and here is Wolfram Helland, who's co-authoring the book, and all these people were here, very, very knowledgeable people in the area of glass ceramic. Okay. And these are very interesting, important people in the area of glass ceramics. I'm not going to name all of them, but I'm using this opportunity to invite you to the next symposium in the series of crystallization. Will be this year in Japan, Nagaoka, and this symposium will be chaired by Professor Taka Komatsu. I'm going to talk more about Professor Komatsu. He is a great, great expert on laser crystallization of glasses, and I do have some slides about his research. So if you're really interested, this is a must-attend symposium this year for you. Okay. Now, there are several other important books about glass ceramics. Okay, to my great surprise, there are two brand new books. There's a book now from French authors, Daniel Neville and Laurent Cormier, Lionel Montaigne, and other authors. They assembled a very, very interesting book from the fundamentals to applications with more than 600 pages, which is going to be in the market, I think, in May. I think the English version. They already have a French version. The English version will be ready, I think, for Miami, for the Miami meeting. I know of this book because I wrote the preface of the book. Otherwise, I would not know about it. And there's another new book by Professor Margusian in Iran, Nanoglass Ceramics, Processing Properties and Applications, in addition to the classical books that you probably know, the glass ceramic technology, glasses and glass ceramics for medical applications, this Trinad's book on glass ceramic materials, low expansion glass ceramic, and this was one of the first books from the late Professor Peter Macmillan on glass ceramics. There are also interesting review articles by George Peel and Linda Pinckney, Wolfram Holland, Wolfgang Panhorst, Peter James, Mark Davis, and other important people in the area. So there's lots of good published material in that area. Let's take a look at some statistics. A recent database search indicated that there are already from 7,000 to 13,000 articles published with the keywords in either abstracts or title. So the real number lies in between. Maybe 10,000 really dedicated articles on glass ceramics have been published so far. 10,000 articles focusing on glass ceramics, scientific articles. Later on, I'm going to talk about patents. And if you see the evolution of this number along the years, it all started in '53, but the first article was published probably in 1960 or so, and then the numbers continuously increased. There are two curves, because this one is taking the word glass ceramic only in the article title, and this other one taking either the glass ceramic keyword in the title, abstract, or keywords. But so the real number could be somewhere here, continuously increasing. So it's a very active research area still, despite the fact that these materials were discovered 60 years ago. Okay, so let's then take a look at some critical issues regarding glass ceramic processing. But I think this could be a little bit boring, so I decided to show different types of glass ceramics, and then while describing each type of glass ceramic, I'm going to mention a little bit how they're processed. So I believe this way be more interesting than only describing different processing techniques that are used to induce controlled crystallization in certain glasses. Okay, are you still with me? I'm on slide number 21. Everything on slide 21?
We're still here on slide 21.
Okay, Bill, thank you. Right. Okay, this is very basic. I'm sure you have seen this figure 1,000 times. This is perhaps the most important figure in glass science. The phenomenon of glass transition and crystallization. If you recall one of the first slides about the most frequent keywords, the number one was crystallization, number 2 was glass transition. So this is a very important plot about glass making. And by the way, there are at least 2 books named Glass Transition and 10 books on crystallization or glass ceramics. So these are important phenomena regarding glass making. So let's just briefly, you don't, okay. Start here with a true liquid, and a true liquid only exists about the melting point of the crystal or the liquidus temperature of a mixture. So we have a true liquid, and any true liquid loves to crystallize when they're cooled down below their liquidus, because the crystal is the thermodynamic stable phase. So giving enough time, all liquids will crystallize. But we are glass scientists, so we like to fool Mother Nature. How we do that? We pick certain compositions which are particularly reluctant to crystallize. In that way, one can cool down the liquid, avoiding crystallization, and then, if you really look, you reach a point where the internal relaxation times of the molecular unities which fill the liquid cannot any longer follow this line here, cannot follow, so it freezes into a glass. So a glass is indeed a liquid which was frozen. The structure of the glass is very, very, very similar to the structure of its isochemical liquid. Okay, we made a glass successfully, but for some cases, for instance, to increase the toughness, we want to crystallize that glass in a controlled way. So we normally heat treat this glass a little bit above the glass transition, but you can also crystallize below the glass transition. You just have to wait longer. You also crystallize below. We did this many times in the lab. And wait for some time, and then one arrives at a polycrystalline material denominated glass ceramic. So it's all here. But the main questions are how to pick a good enough composition to make a glass so it cannot be a reluctant glass-forming composition. It has to be, to make a, say, a commercial glass ceramic on scale, large volumes. The original parent glass composition must be chosen to be a relatively good glass-forming material. And at the same time, it must somehow be able to crystallize after being heated properly. So it has to have some sort of nucleating agents or not. Some compositions do not actually need a nucleating agent, but most do. So to get, for instance, a very fine microstructure to make a transparent glass ceramic, for instance. So you need a good glass forming composition, which can be made into a glass, but later on, it has to be crystallized. So it's not a very trivial task to find or to select good compositions. And then you also want some crystal phases which have appropriate properties. For instance, to be bioactive, or to be electrically, ionically conducting, or to be an insulator, or to have a zero thermal expansion coefficient, something like that. So you also, in addition to these requirements, one has to choose the crystal phase or phases which are going to be formed in this glass ceramic. And then one has to choose the thermal treatments which will induce a plethora of nuclei or only a few nuclei, one phase, two or three crystal phases. So it's a big game involved. There are 60 years of accumulated experience in this area since Stuke started, so we are not going to learn everything in 2 hours. You are aware of that, but we do our best to give you some critical issues at least. So I'm moving now to slide 23. So this is a very schematic slide showing that, okay, you have a mixture, you've chosen somehow your chemicals, and then you have to melt and get rid of bubbles and homogenize the material to make a nice homogeneous bubble-free glass. Then you have to make some shape, a bottle or a plate or a disc or some part has to be made. And then one has normally to nucleate the appropriate crystal phase, and then even a second treatment for growth. Sometimes these two treatments can be combined into a single treatment, or in other occasions you have to split them into 3 or 4 different treatments. In the end, if we pick a correct composition, a correct thermal treatment, end up with a nice glass ceramic after cooling down. Some people have managed, for a few compositions at least, to go directly from the melting, from the shaping to a glass ceramic, allowing a certain cooling path which will allow simultaneous nucleation growth without the need of stopping for nucleation growth treatments. So each type of glass ceramics demands a certain thermal treatment. These are the kind of default type of treatments, nucleation growth, but there are several others which have been patented or published or kept as an industrial secret by glass ceramic makers. Okay. Any questions so far for this part? I'll wait for a minute or two, see if there are any questions.
Are you ready to pick up on that question that came earlier, or do you want to wait till you cover it in your lecture?
I want to move on because I'm going to cover mechanical properties, so a little bit more for that question. But at this point, I like to pick any questions regarding the stuff that I have covered so far.
Okay, there's a question from El Sayed.
El Sayed, Padova. Como está? Starting from glass powder and after shaping a scaffold by direct printing, how dense can be obtained avoiding crystallization? Okay. This is indeed an extremely difficult question. By the way, we work here with scaffolds, so I have personal experience with scaffolds. You see, you're dealing with sintering and crystallization. In making a scaffold, you have a glass powder. Your ink is a glass powder. So when you heat it up for sintering, surface crystallization starts immediately. So there is a competition between viscous flow sintering and surface crystallization. And the whole game is, if it crystallizes too fast, you can no longer sinter by viscous flow because there's no more viscous flow. So in the second lecture on Tuesday, I think I'm going to expand a little bit on sintering versus crystallization. And there is one model at least, the clusters model. I'm not sure if you have seen these papers by Miguel Prado and Ralph Miller and myself. The clusters model for glass sintering with concurrent crystallization. So you need to know the particle size, the average particle size at least, the viscosity of the glass, the surface tension of the glass, then the crystal growth rate of whatever crystal phases grow in that particular glass, and the number of active sites per unit surface area. Independently, you need to measure independently all these 5 properties, and then you can model, at least one model, you can use this clusters model. You can do it isothermically, non-isothermically, to see if sintering and densification will prevail before surface crystallization. I'm going to talk more about this a little bit ahead, but it's very difficult to control this process. Okay, I guess I have to move on now. Oh, this is in Portuguese. Yeah, I apologize. Only now I realize this is really in Portuguese, but I'll try to translate this to you. Well, okay, this is so simple. You have to mix whatever chemicals have been chosen, add some nucleating agents, which are effective for that particular chemical composition. And by the way, nucleating agents are very specific. Each glass ceramic demands a different type or different combinations even of nucleating agents, such as chromium oxide, titania, zirconia, metallic particles, iron oxide, P2O5, certain oxides and metallic particles have been shown to be effective nucleating agents, but it's very, very difficult to predict. I'm not sure if anybody is able to predict if a certain nucleating agent will be effective for a given glass composition, so it has to be tried empirically in the lab. Anyway, and also how much nucleating agent you have to add. In principle, the minimum possible amount to avoid messing up all the other properties of the glass, because you normally dissolve these nucleating agents in the glass melt and then they precipitate when you heat treat. Then you have to melt, homogenize, refine, then you have to shape the article, and there are several ways, then the thermal treatment, then cool down. So this is basically the same thing as I had in the previous slide. So I'm going to move on. This is in Portuguese anyway. Although there are many Brazilian, Italian, Spanish speaking, I can see, so the Italians can read this. Certo? Okay. This is again the sintering route, but it's in Portuguese. I'm going to skip it. Later on, I'll be back to the sintering route. Okay. What are glass ceramics? I don't know. I have to ask George Pugh or Paul van Hollen, these big guys, because even I don't know exactly if, can you call a material which has only, say, 1% of crystals embedded in a glass matrix, a glass ceramic, or there is a certain minimal amount of crystallized volume fraction one needs before you can call a glass ceramic? Myself, in our group, we don't make any distinction. Anything, any glass which has a minimal amount of crystals, we call glass ceramic. I'm not sure if there's a definition for that, but within the framework of these lectures, I'm calling glass ceramics anything which contain a residual glass phase with one or more crystalline phases with widely varying crystallinity from 0.5% to 99.5 or even 100% crystalline. But most frequently, commercial materials have between 30 and 70% of crystalline volume fraction in a residual glass matrix. And I must tell you here that the glass matrix, the properties of the glass matrix are very important also. So the overall properties of a glass ceramic depend upon the properties of all of their crystal phases, but also of the properties of the residual glass phase. And this is actually the topic that the TC7 guys are working at the moment, the role of the residual phase, glass phase. The advantages of glass ceramics, they can be produced by any glass forming technique, in principle, because you have to produce a glass first, and then just heat treat that glass without letting it sag. You know, that's why internal crystallization is important. So the whole thing crystallizes simultaneously. If you start with surface crystallization, you have a thin layer of crystals formed on the surface, but the bulk of the material is glassy. So that's why it sags, like in Vermeer's experiments more than 200 years ago. It's possible to design. I teach here in the materials engineering course, and I tell our students that the ability to design a micro or nanostructure is in the core of a materials engineer. A materials engineer, in principle, is not able to design the external shape like a big beam of concrete, reinforced concrete, but he can design the microstructure of the concrete to be resistant to seawater or thermal shock or acids or whatever. So, and the glass ceramics is one of the technologies, one of the processing technologies which allow, in my opinion, the most flexible, one of the most flexible techniques to design a materials microstructure. You can design the type of glass phase, the type of crystals, the crystal size distribution, textured versus non-textured microstructures, and porosity, non-porosity, etc., etc., etc. Oops. Most have zero or low porosity, but I must tell you, most people think that if you start with glass, which have no pores, so you think that you end up with a dense material. Well, in many situations, quite frequently, crystallization leads to pores. And there are several reasons for that. One reason is that the density, sometimes the mass density of the crystal phase is so much larger than the density of the parent glass that you have a local porosity forming. Or in other situations, gases are dissolved in the glass, such as CO2, SO2, oxygen, etc., water, OH. They're dissolved, but when the glass starts to crystallize, they're no longer dissolved, or their solubility limits are smaller in the crystal phases, so there's nucleation of bubbles during heat treatment. We have seen this many times. Although very few people have reported studies in that area. That's an open area, I think, for studies. And finally, it's possible to combine properties. This is a nice thing about glass ceramics. You can combine properties such as, for instance, transparency indivisible with zero thermal expansion coefficient, something like that. Properties can be combined. It's a nice feature of glass ceramic. Well, at this stage, I believe you are convinced that I like glass ceramics. I really like these kind of materials. Okay, microstructural design, grain size distribution, crystal shape, texture, non-texture, porosity, percentage of crystallinity, type, and number of phases. This design, of course, they're governed by the chemical composition, by the nucleating agents which are added, and by the thermal treatment. These are the variables. Parent glass, nucleating agents, thermal treatment. The variables you can play around. And you can have high thermal and chemical stability. And here, starting to answer that question, the toughness of glass ceramics, of most glass ceramics that I know, vary from 1 to about 5 megapascal square root of meter. And the toughness of glasses is 0.5 to 0.7. So glass ceramics are in general much tougher, 10 times tougher, usually 10 times, 5 to 10 times tougher than glasses, which is good. So if you recall, this is one of the most negative properties of glass is their fragility, low toughness. Electrical properties can be controlled from highly insulating. There are high-tension insulators made of glass ceramics to ionically conducting glass ceramics. They can be optically transparent, translucent, like teeth. Artificial teeth are being made by the glass ceramic root, and they are translucent. And most glass ceramics, of course, are opaque because of light scattering. Even tempered glass. Yes, Richard. Glass ceramics can be stronger, and they're definitely tougher. They're definitely tougher than tempered glass. Tempered glass is not tougher. It's tempered glasses, due to their residual stress fields, they're stronger, but they're not tougher. Glass ceramics are tougher. They resist, once a crack starts to propagate, they resist. There's an intrinsic resistance to crack propagation in glass ceramics. In a tempered glass, once a crack starts to propagate, boom, that's it. So tempered glasses are very nice. I have tempered glasses in my house extensively. I love those materials, but they're not tougher or stronger as some glass ceramics. The difficult thing is to make a transparent and tough glass ceramic. This is more difficult, but it's not so difficult to make opaque, stronger glass ceramics. There's another question, composite from different components which can crystallize. Let me see the previous question from Padova, El-Sayed from Padova. Composites from different components which can crystallize by heat treatment with some oxides, we can call that glass ceramics. Good question, El-Sayed. I believe that it depends on the processing route. If you have a crystalline material, you add some glass forming components, and for instance, hot press to make a composite. That is indeed, in the end, we will have a glass phase and some crystal phase. But that's not a glass ceramic. It was not made by the controlled crystallization kind of route that we discussed. But if you're saying that if you make a composite which was then crystallized by heat treatment, then yes. If your glass matrix in your composite crystallized afterwards, I think you can call a glass ceramic composite, in my opinion. Okay. Himanshu or Bill, how much longer do I have?
You have 5 more minutes.
5 more minutes. Oh, so I did not even cover the introduction, but okay. We'll need some extra lectures to finish this. Okay. So now we selected a very good composition. We selected nucleating agents. We designed some thermal treatments, and these are the kinds of nano or microstructure that one can have. There's a whole range of microstructures that one can have with this route, and of course they can be designed, and they lead to interesting properties. But there are also problems. If you look here in this particular microstructure, there's a glass phase, one crystal, in this particular case, one single crystal, and cracks being nucleated. So another problem related to glass ceramic processing is that the thermal and elastic properties of most crystals are different from the thermal and elastic properties of the residual glass phase. If they are above a certain critical limit, and this can be even calculated, and people have published on this, you can calculate these residual stresses, the level of residual stresses, and they can lead to spontaneous cracking, which is no good in most cases. But this can be calculated and measured. So, I was going to start then to describe a number of types of glass ceramic products, such as hard disk substrates, huge telescopic mirrors, cooktop plates, artificial teeth, and commercial products like those. And in discussing these products, I am going to briefly mention how they are processed. That's the idea, I guess, for Tuesday, because I'm running out of time, so it's perhaps a good idea to take on some more questions. Himanshu, just let me know how you want to do this.